Is there anything in this vast, wonderful universe that doesn't move? Is there any piece of reality that can sit still, absolutely still, and say, I am at rest? And if the answer is no, if everything from the tiniest dust grain to the greatest galaxy is in a state of perpetual motion, then why? What kind of universe have we found ourselves in where stillness is forbidden? Now, before we even attempt an answer, before we dive into the crazy, beautiful laws that run this place, let's not rush. Let's pause. Let's look at something ordinary. I want you to look at this glass of water. It looks very peaceful, doesn't it? It is absolutely still. It is quiet. It is not going anywhere. If you were a poet, you would say the water is at rest. But I am a physicist. And because I am a physicist, I cannot help but look at this glass and see a lie, a beautiful lie, because your eyes are playing a trick on you. They are too crude. They are too slow. They act like a camera with the shutter left open too long, blurring everything out into this smooth, quiet picture. But if we could dial up the magnification, if we could look at this water 1 billion times closer, down to the scale of the atom, God, what a monster we would see. It is not quiet. It is a catastrophe. Inside that still water, there are molecules, billions upon billions of them. And they are not sitting there politely. They are crashing into each other. They are banging and twisting and turning. Every single molecule is hitting its neighbor trillions of times a second. It is a mosh pit. It is a riot. They are jiggling with a tremendous amount of energy. If you could hear it, it would be a roar louder than a jet engine. But because the jiggling is random, because one hits left and the other hits right, it cancels out. On the big scale, the water stays in the glass. So the stillness is just an illusion of the average. It is just the fact that the chaos is happening too fast for you to see. Now you're smiling. You are thinking, okay, that is the water. The water is a liquid, but I am solid. I am sitting in this chair. The chair is bolted to the floor. We are not moving. Are you sure? Let us check the measurements. First, you are on the earth, and the earth is spinning. So right now, just by sitting there, you are moving at about 1,000 miles an hour around the axis of the planet. But that is peanuts. That is slow, because the earth is also taking a trip around the sun. To make that trip in 1 year, we have to move at 67,000 miles an hour. 67,000. If you were in a car going that fast and you hit a wall, you wouldn't just die. You would vaporize. The heat would be so intense you would turn into a cloud of glowing plasma. But we are not done, because the sun is not sitting still either. The sun is drifting. It is bobbing up and down through the Milky Way galaxy. And the galaxy is falling. It is falling toward the Andromeda galaxy, and it is being pushed by the expansion of space. When we add it all up, when we measure our speed against the background of the universe itself, the cosmic microwave background, do you know how fast we are going? 825,000 miles per hour. Since I started talking 2 minutes ago, you've traveled nearly 30,000 miles. You are on a spaceship without a windshield. So here is the mystery that should keep you awake at night. Why doesn't the coffee spill? When I shake this glass, it spills. But the earth is moving almost 1 million miles an hour, and the water stays flat. Why don't we feel the wind in our hair? Why aren't we crushed against the back of the wall? How can we be moving so fast and yet feel so still? It took a genius like Galileo to figure it out. And the answer he found is the first law of the universe, inertia. It turns out nature doesn't care how fast you are going. Nature only cares if you change how fast you are going. You can go 1 billion miles an hour. And as long as it is smooth, as long as it is straight, you can pour a cup of tea and not spill a drop. There is no such thing as stopped. Stopped is just a word we invented because we are narrow-minded. Stopped just means moving at the same speed as the train you are sitting on. So we have established that everything is moving. The atoms in the water are jiggling because of heat. The earth is spinning because of gravity and momentum. But this leads us to a much deeper question. A question a child would ask. Why doesn't it stop? Everything we make stops. If I slide a piece of chalk across the table, friction kills it. If I turn off the engine of my car, it rolls to a halt. We are used to a world where things run out of gas. But the atoms, they have been banging against each other for 13.8 billion years. They haven't tired out. They haven't lost their energy. The earth has been spinning for 4 billion years. Who is pushing it? Where is the engine? It seems like a simple question. Why do things keep moving? But to answer it, we have to look at the very fabric of reality. We have to look at energy. And finally, we are going to have to look at something very strange called quantum mechanics, because I am going to tell you a secret. We used to think that if you took all the energy away, if you cooled the universe down to absolute zero, everything would finally stop. We thought we could freeze nature into silence. We were wrong. It turns out nature is forbidden from sitting still. It is against the law. Even in the absolute dark, even at absolute zero, there is a vibration, a ghost movement. The universe is doing a dance that it is physically impossible to stop. So buckle your seatbelts. You are moving at 800,000 miles an hour, and we're about to find out why the brakes don't work. Now we have to look at the sky. We have to look at the big things. You look up at the moon. There it is, a big rock hanging in the dark. And if you ask a man on the street, what is the moon doing? He will say, oh, well, it is floating. He thinks that because it is in space, the rules of gravity have been turned off. He thinks space is a place where things just float. And I have to tell you, that is a terrible mistake. It is a misconception that blocks your understanding of the universe. The moon is not floating. The moon is falling. It is falling toward the earth just as surely as an apple falls from a tree. If I take a rock and I let go of it, what happens? Smack. It hits the floor. Gravity pulls it in. The earth wants that rock. Well, the earth wants the moon too. It is pulling on the moon with a tremendous force. So why doesn't it come down? Why doesn't it crash into us and end the lecture early? To understand this, we have to use an idea from Isaac Newton. And it is a beautiful idea. It is a geometric miracle. I want you to imagine a mountain, a very high mountain, ridiculously high. And on top of this mountain, we have a cannon. Now we fire the cannon. Boom! The cannonball shoots out horizontally. It goes forward a mile, and then gravity pulls it down, and it hits the ground. It makes a curve. Now let's use more gunpowder. Let's shoot it faster. It goes 10 miles. It still curves down, but the curve is flatter. It hits the ground further away. Now, and here is the trick, here is the secret. Imagine we shoot it with such tremendous power, such incredible speed that it goes halfway around the world. It is still falling. Gravity is still pulling it down towards the center of the earth. But because the earth is a ball, because the earth is round, the surface of the earth is curving away underneath it. If you shoot it fast enough, about 17,000 miles an hour, the ball falls down exactly as fast as the earth curves away. It never hits. That is what an orbit is. The moon is falling around the earth. The earth is falling around the sun. The sun is falling around the heavy center of the galaxy. It is a permanent state of missing the ground. So you see, motion in the universe is a balancing act. On one side, you have gravity, the great pull. It wants to crush everything together. It wants to bring all the matter back into a tight little ball. On the other side, you have sideways motion, momentum. The universe we live in, the solar system, the galaxy, is the peace treaty between these two. But you might ask me, and you should ask me, you should be critical. Professor, okay, they are orbiting, but why did they keep doing it for billions of years? Why don't they slow down? If I roll a ball on the floor, it eventually stops. Why? Because of friction. Because the air bumps into it. Because the floor is rough. But space is the ultimate greased road. There is practically no air. There is no friction. There is nothing to rub against. This is the law of inertia. Once you get a planet moving, it is like a car on ice with no brakes. It just goes, and it goes, and it goes. It remembers the push it got 4.5 billion years ago. And where did that push come from? This is the part that is really fun. This is the part about the spin. Look at the universe. Everything is spinning. The earth spins. The sun spins. The galaxy is a giant spinning plate. Why? Why not just move in a straight line? It has to do with something called angular momentum. Imagine a figure skater. You have seen this on television, so she starts spinning with her arms out. She is going slowly, round and round. Then suddenly she pulls her arms in tight to her chest. What happened? She speeds up. Whiz! She becomes a blur. She didn't add any energy. She didn't turn on a motor. She just changed the distribution of mass. Nature has a rule. If you shrink a spinning thing, it must spin faster to compensate. The amount of spin, the angular momentum, must be conserved. Now rewind the clock. Go back 4.5 billion years. Before the earth was a rock, it was a cloud. A giant, distinct, messy cloud of gas and dust. And this cloud was drifting through space. And just by accident, it had a little bit of a drift, a tiny little rotation, just a little swirl. Then gravity took over. The cloud started to collapse. It started to fall inward on itself. It got smaller and smaller. And just like the figure skater pulling in her arms, that giant cloud had to spin faster. The little swirl became a hurricane. The hurricane became a disk. The center became the sun. And the leftovers became the planets. And we are still spinning today. We are spinning because we are the leftovers of that collapsing cloud. We are preserving the motion of the birth of the solar system. So to answer the question, why is the universe in motion? For the big stuff, the answer is history. We are moving because we were pushed by gravity a long time ago, and there is nothing in the empty vacuum of space to stop us. We are riding the echo of a collapse that happened before life even existed. But I look at your faces and I see you are not satisfied. And you shouldn't be. Because I told you about the planet. I told you about the stars. I told you about the dead things that fly through the vacuum. But what about the live things? What about the water in the glass? What about the air in this room? What about your own body? You are not spinning at 17,000 miles an hour relative to the floor. You are sitting still, but you are warm. If I touch your hand, it is hot. What is heat? We say heat is energy, but that is just a word. That doesn't tell us what is actually happening. If we look down at the atoms, why are they moving? They aren't orbiting anything. They aren't falling around a planet. So why do the atoms jiggle? If I cool them down, if I put the universe in a freezer and I wait 1 billion years, will the atoms finally stop? Will the universe finally freeze into a perfect, motionless photograph? The answer, it turns out, is the weirdest thing in all of physics. The answer is no. Nature refuses to freeze. And to find out why, we have to leave the world of Isaac Newton, and we have to go down into the basement. We have to go to the quantum world. So we have the planets spinning because of history. They are just coasting. That is easy to understand. But now I want to come back to the room. I want to come back to you. You are not coasting through a vacuum. You are sitting in a soup of air. You are made of water and carbon. And if I put a thermometer under your tongue, it says 98.6. You are hot. The air in this room is 70 degrees. It is warm. The coffee in my cup is 150 degrees. It is painful. Now, what is that? For thousands of years, people, smart people, philosophers, thought that heat was a substance. They thought it was a fluid, like a magical juice that flowed from the fire into the pot. They called it caloric. If you had a lot of caloric, you were hot. If it leaked out, you were cold. It sounds nice. It makes sense to our intuition. But it is completely wrong. We know now, and we know this for certain, that heat is not a thing. Heat is a verb. Heat is just a word we use to describe motion. It is the jiggling. I want you to change your mental camera again. Zoom in on the air in front of your nose. Nitrogen, oxygen. They are not floating. They are bullets. At room temperature, the air molecules are moving at roughly 1,000 miles per hour. They are smashing into your skin constantly. Bam, bam, bam. Why doesn't it hurt? Why don't you feel bruised? Because they are tiny. And because there are billions of them hitting you from all sides, so the pressure is even. But what happens when you make the air hotter? All you are doing is stepping on the gas pedal. You are putting energy in and the molecules speed up. Instead of 1,000 miles an hour, they go 2,000. They hit you harder. They hit you more often. That ouch you feel when you touch a hot stove, that is not magic energy entering your finger. That is billions of metal atoms punching the atoms of your skin so hard that they break your biological machinery. It is a microscopic car crash. So heat is motion. But wait a minute. You say, Professor, the air is a gas. Gases fly around. I get that. But look at this table. It is solid wood. It is hard. It isn't going anywhere. But it still has a temperature. So how can the wood be moving? This is where nature gets really clever. Imagine a bed spring, a coil. In a solid, the atoms are not free to fly around like in a gas. They are stuck. They have a designated seat. They are arranged in a nice, neat grid, the crystal lattice, but they are not glued down. They are connected to their neighbors by invisible springs. These springs are the electromagnetic forces holding them together. So what happens when a solid is warm? The atom sits in its chair, but it shakes. It vibrates. Wiggle, wiggle, wiggle. It pulls on the spring, and that pulls on the neighbor, and the neighbor wiggles too. A solid is just a shimmering, shaking grid of atoms. If I heat up a piece of iron, the atoms shake more violently. The springs stretch further. If I heat it enough, the shaking gets so violent that the electromagnetic springs can't hold on anymore. The atoms break loose. They start to slide over each other. What do we call that? Melting. The iron becomes a liquid. And if I heat it even more, they fly apart completely, boiling. So every phase of matter, solid, liquid, gas, is just a description of how much the atoms are shaking. Now, let's play a game. Let's do a thought experiment, like if heat is motion, if hot means fast, then cold must mean slow. Let us take a glass of water and put it in a machine, a super refrigerator. We start sucking the energy out. We steal the heat. The atoms slow down. The liquid turns to ice. The springs lock into place, but the ice is still vibrating. So we cool it more, minus 100 degrees. The shaking gets softer, minus 200 degrees. The shaking is a gentle hum, minus 270 degrees. Deep space. We are getting very close to the bottom of the scale. We are getting close to the place where the graph hits the floor. We call this absolute zero, 0 Kelvin. In the old days, using classical mechanics, using the physics of Newton, we believed that if you reached absolute zero, the motion would stop completely. The atoms would stop vibrating. The springs would go still. The universe would become a perfectly still, perfectly ordered, frozen graveyard. Everything would just pause. It is the logical conclusion of the definition of heat. No heat equals no motion. But here is where the universe plays a trick on us. Here is where the story takes a sharp left turn. Because when we actually try to do this, when we build our lasers and our magnetic traps and we cool atoms down to a billionth of a degree above zero, we find out that we can't get to the bottom. Nature fights us. It is like trying to walk halfway to the wall and then halfway again. You get closer and closer, but you never touch it. Thermodynamics forbids us from reaching perfect zero, but that is not the scary part. The scary part is, even if we could get there, even if we could suck every single calorie of heat out of the universe, even if we could make it colder than the deepest void, the atom would not stop. They would not freeze into a photograph. Instead, they would do something impossible. They would start to blur. They would start to jitter. They would start to exist in two places at once. We thought we were looking at a simple machine that was running out of fuel. But as we turned the lights down, we realized there is something else keeping the engine running. Something that has nothing to do with heat. Something that is built into the basement of reality. We have found the door to the quantum world. And behind that door, stillness is illegal. So we have dialed the temperature down. We are at absolute zero. The classical physicist, the guy from the 1800s, he says, okay, the party is over, the lights are out, the atoms should stop moving. They should sit in their assigned seats and be quiet. He thinks the universe is like a game of musical chairs, and when the music stops, everyone sits down. But the quantum mechanics and the new physics says no. It says that if you turn off the music, the chairs disappear and the players start flying through the wall. To understand why, we have to talk about a man named Werner Heisenberg. He discovered a rule that is not about clumsy measurements. It is not that our rulers are too thick or our eyes are too bad. It is a rule about reality itself. It is called the uncertainty principle. Now, people get this wrong all the time. They think it means everything is uncertain. That is philosophy, not physics. The physics is very specific. Heisenberg said you cannot know two specific things about a particle at the same time with perfect precision. You cannot know its position, where it is, and its momentum, how fast it is going. It is a seesaw. It is a trade-off. If you focus the camera to see exactly where an electron is, the electron gets fuzzy about how fast it is moving. If you measure exactly how fast it is going, You lose track of where it is. The more you squeeze one, the more the other spreads out. Now, do you see the problem with stopping? Think about it. What does it mean to be stopped? What does it mean to be perfectly still? It means I know exactly where you are. You are right there at point X. And it means I know exactly how fast you are moving. You are moving at speed 0. To be stopped is to have perfect position and perfect zero momentum. Heisenberg says that is illegal. Nature forbids it. If you try to pin an atom down to a precise spot, if you try to freeze it, its momentum must become uncertain. An uncertain momentum doesn't mean maybe it's moving. It means it fluctuates. It jumps. It jitters. The energy shoots up to compensate for the position being pinned down. I like to think of it like this. Imagine you have an atom in a box, and the atom is bouncing around. Now you make the box smaller. You squeeze it. You are forcing the uncertainty of the position to get smaller. You are pinning it down. So what happens to the momentum? It has to get bigger. The atom starts hitting the walls harder. Bang, bang, bang. The tighter you squeeze it, the faster it moves. You are trying to crush it into stillness, but the uncertainty principle fights back. It creates a pressure. This is actually the reason you and I exist. Why doesn't the electron fall into the nucleus? The nucleus is positive. The electron is negative. Opposites attract. Gravity pulls the earth to the sun, and electricity pulls the electron to the proton. Classically, the electron should radiate its energy away, crash into the center, and the atom should collapse. Matter should shrink down to a pinprick. Why doesn't it? Because as the electron gets closer to the center, it's getting confined. Its position is getting more precise. So its speed gets wilder. It starts to dance. It starts to vibrate with tremendous kinetic energy. It cannot fall in because the uncertainty principle forces it to keep moving. It creates a cloud of probability. The atom is inflated by its own refusal to sit still. So let's go back.